I really like this example because we're going to do a pretty abstract analysis of the situation. There's almost no numbers in this problem. We're just going to study a situation by analyzing its derivatives. So let's jump into it. We have a tank of propane that has hemispherical ends to a right cylindrical body. So let's just get a picture of what we're talking about here. I've got some sort of right cylinder with circular ends. And on those ends are cylinders, or sorry, hemispheres. So pretty much like half spheres. All right, let's give some names to things. Let's call this the length. And the only other measurement involved in this is the radius, or how wide that cylinder is. Right, the radius of from where the cylinder ends to the end of the sphere. Okay. So we've got sort of that situation going on, and we can start studying it. If we increase the length of the tank by 0.1 meter, estimate how much the volume changes. So we're interested in the relationship between the volume and the length. Let's first find the volume equation. The volume equation will be the volume of this right circular cylinder. So that will be pi r squared times the length. And we will add to that the volume of, let me switch colors, of these hemispheres. And if I take two hemispheres and I put them together, I make one sphere. And the volume of a sphere of radius r is given to us by 4/3 pi r cubed. All right, so there's my volume. And I'm interested in the change in the volume as I change the length. Right, this problem asks me if I increase the length of the tank, what happens to the volume? So I want the relationship between volume and length. Let's differentiate. If I differentiate my volume equation with respect to the L variable, we have a pi r squared in the first term, and then plus a nothing in the second term because there's no L's over there. It's a constant as far as L is concerned. So it's just pi r squared. And we can move the dl onto the other side and find that the change in the volume can be given by pi r squared times dl. So just to tie this back into tangent lines and differentials, we're not going to do this in this problem, but you can find, so if dv is equal to pi r squared times dl, you can estimate the actual change in the volume with the derivative of the volume. So that'll be pi r squared times a L minus L naught, right? A change in L. And then if your change in volume has like a volume minus the initial volume, then you can just throw that V naught onto the other side as well. And that's your initial volume plus pi r squared, your derivative, times L minus L naught. So that's exactly just your tangent line. But that's neither here nor there. Here, this is where I want to stop. So the change in my volume can be given by the derivative of my volume with respect to L times the change in L. Now, our change in L is equal to 0.1 meter. That's given to us in the problem. Okay, so let's move on. We're going to come back to that. The second question, a very natural second question, is what happens if I change my radius by 0.1 meter? So I'm going to change either my length or my radius by the same amount, and I want to study which has a bigger impact on my volume. So let's just copy down the volume equation. Volume was pi r squared times L plus 4/3 pi r cubed. And now we want to study how our volume changes with respect to the radius. And differentiating the volume equation with respect to the r variable, we have 2 pi r times L plus 4 pi r squared. And we'll do the exact same thing. Let's throw that dr onto the other side. And use the fact that our radius is changing by 0.1 meter. So positive 0.1. The change in the volume is given by 2 pi r times L plus 4 pi r squared times a 0.1. Okay, so let's just talk about what we just showed ourselves. Which is going to have a bigger impact on the volume, changing the length or changing the radius? Both of them have a 0.1, so we can kind of just ignore that. Whichever one has a bigger leading constant right there is going to be the bigger number. So if we look at my change in the volume equation as I change my length, I have a pi r squared right there. Well, I also have a pi r squared right there. In fact, I have 4 of them. And then I'm also adding that positive term over there, the 2 pi rl. So this is definitely a bigger number than this. So we just told ourselves that if you want to impact your volume the most, you should change the radius of the tank rather than the length, because the radius has a larger impact on the volume than the length does.